Hi, everybody. Welcome to the final presentations for the Earth Analytics Foundation's Professional Graduate Certificate. We have one group of three and two individual projects here today. And these guys have been working really hard since about March on these projects with their partners. And I'm seeing some of the partners here as well. So it's great to see you, and thank you so much for your help with this. And I'm gonna let the students take it away. Yeah, this is always our favorite part of the year. So I am gonna do you guys first.
Hello, everyone, and welcome to our presentation. We're going to talk about how we developed an app to locate canopy gaps in forest land for management to use. Next slide. My name is Christopher Griego. I am a New Mexico Tech graduate for Earth Science, and I'm currently pursuing a graduate certificate for Earth Data Analysis at University of Colorado Boulder. If you guys want to introduce yourselves.
I am Ed, also part of this certificate program too, like Peter and Chris. I have a day job as a fintech consultant. I'm here to learn how to apply my skills in a different domain and looking for part-time academic opportunities to grow.
And I'm Peter Kobolars. I am an environmental consultant and I focus on GIS, and I also am a student in the Earth Data Analytics Certificate Program.
So this app was commissioned to us by the Watershed Center. They're just a nonprofit independent organization dedicated to helping maintain and restore the local watershed areas around Boulder, Colorado. And they were needing something to help with maintaining their project areas, a lot of forest land. So we decided we would help them out with that. Next slide. So what we're focusing on is what's called forest heterogeneity, which is basically just about how much diversity there is in the forest structure itself. To put it more in layman's terms, it's just about what's where are the bushes, where are the trees, where are the gaps. This is very important for measuring the overall health of an ecosystem. And in regards to what we're doing, we're mostly looking at wildfire management, to help people who are managing, identify areas where there's overgrowth that need treatment, so that the wildfires don't spread as easily, with the ultimate goal being to sort of try to restore the treatment areas to what it would have been like before European settlements. Next slide. And just to define what we're talking about, basically canopy is where there are trees and the gaps is where there's not trees. And we're trying to basically write software that would differentiate that. And our objective is to basically create a user-friendly tool, because a lot of this is very time-consuming and tedious. And pretty much all the tools available required user input at some degree. And we were trying to achieve this with machine learning to just save a lot of time and effort on behalf of forest management people.
For this effort, we focused on the Left Hand Creek watershed, which is within the responsibility area of the Watershed Center. This is a watershed in the Front Range, northwest of Boulder and southwest of Longmont. And we were fortunate that this area is part of some very good high quality data acquisition projects, specifically the Denver Regional Council of Governments 2020 imagery project, which had both 6-inch and 12-inch resolution throughout the study area shown here. And also there's a high quality LiDAR project that was acquired by the same organization in 2020, which covers most, if not all, of the Left Hand Creek watershed. So these are our two primary data sources. There's two workflows. One focuses on image segmentation using the aerial imagery. One focuses on LiDAR processing. LiDAR is not available everywhere, but if it is, our workflow can use both. And if only aerial imagery is available, that works too. There were 4 project areas that we used as our test cases, highlighted in red on the map, ranging in size from 8 acres to 1,500 acres. Now Ed will talk about our project workflow.
Thanks, Peter. I'm going to go through a few slides on the workflow, and the workflow is really trying to answer these questions. Where are the trees and where are the tree gaps? Starting with data preparations. Next slide. So on the screen, you can see 2 pictures illustrating the results of identifying the imagery tiles to download. Our steps involves finding the intersecting tiles blue and the bounding box black of the area of interest red. Next slide. Once you have the downloaded tiles, we can crop them by bounding box or by area of interest in preparation for data analysis. This step reduces the tile size to the smallest area possible before the next step. Next slide. And we follow a very similar process on later tiles. Next slide. Moving forward from data preparation is to analyze the data through image segmentation and LiDAR processing. Specifically, the segmentation method involved 5 steps for the imagery tiles. First, calculating the NDVI pixel by pixel, then using the quick shift method from Scikit image to group similar pixels into larger segments. Next, calculating the mean NDVI for each segment. After that, applying the k-means clustering method on the NDVI means. Finally, classifying as trees or not trees. The primary reason for creating segments is to reduce the computational needed for k-means clustering, which is more expensive than calculating NDVI alone. As you can see in this example, we reduce 1.6 million pixels to around 5,000 segments. Next slide. And the reason we cluster on NDVI means is to label each segment as trees or not trees. By assuming that a higher NDVI mean corresponds to trees. And then to you, Peter.
All right, I'll discuss the LiDAR workflow that we developed. So the first step is processing the raw LiDAR data, and these are available in LAS format. And this is the standard binary format for LiDAR projects. And that contains coordinates, returns, intensity, and other metadata. There's a number of ways to process LiDAR data using Python, and we settled on using something called Whitebox Tools, which is an open source geospatial toolbox. And we focus primarily on we care about the first return of the LiDAR, which would reflect the height of the canopy, and the ground return of the LiDAR, which would reflect on the bare earth elevation. So in order to do this, we process the raw LAS files into DEMs, the first return or the canopy, and also the ground return, and then we subtracted those from each other to develop a DEM that reflected the height of everything above the ground. And by classifying on elevation, we used 5 feet above the ground by default. We were able to pull up to develop this DEM that shows an approximation of the canopy. And this was done using a method called IDW interpolation. The raw canopy data has a lot of noise in it, which makes sense. There's gaps in between leaves and branches, but that's not really useful in terms of what we're trying to accomplish here. We don't need a bunch of small gaps identified. We want gaps. We want continuous canopy and then continuous gaps. So there's a cleanup process that we did using spatial analysis to resolve this issue. What we did was apply a buffer to the edge of the canopy, and 5 feet is what we used by default. And in this picture, you can see that buffer was used to clip out the remainder space to identify gaps. So the green's the canopy, the blue is the 5-foot buffer off the canopy, and the orange is the gaps. And those were output to shape files after we calculated the area of each distinct polygon and categorized them into the categories listed here at the request of the Watershed Center. Those are useful categories for their management practices. Comparing the two results, LiDAR and image segmentation had similar output. However, the LiDAR seems to have a larger area calculated as canopy. And these are a couple examples of where that happened. The top one, the red outline is, it's like a stream and riparian area. So the height of that canopy was probably less than 5 feet. However, it is green, so it was identified using the NDVI method of image segmentation. And you can tune the LiDAR by adjusting your height parameter, and you can tune image segmentation by adjusting your NDVI mean parameter. This table just shows the output. About approximately 1 acre more was calculated using LiDAR than image segmentation, and that's on a 34-acre site.
All right, so to tie all this together, we started building a QGIS tool to basically give a graphical user interface for people that aren't so technically inclined that they don't want to have to pour through hundreds of lines of code. And so what you see here is just the interface for it. You load in the boundary polygon that defines the study site. You load in whatever raster, which in our case is the aerial photography that we use K-means, or you load in whatever LiDAR set you're wanting to work with, which is the same thing that we were working with. And then these buttons below basically just run the analysis that we had been running in the back end, but just implemented into QGIS. At the moment, we're still trying to debug this because there were a lot of unforeseen challenges that came with trying to integrate into QGIS, but we should have this done within about a week or so.
Great. Thanks for listening to our presentation. Our GitHub repository is available at this URL. And as Chris mentioned, the QGIS tool is not available yet, but will be soon. So if you're interested in following up on this, please reach out to us at the contact information here.
All right, thanks so much to your team. Does anybody have any questions?
Hi, do you think they can hear me? Okay. Oh, you're right here. Oh, I missed the intro. That's exciting. Anyway, I was wondering if you thought about, my understanding, I was taking some notes, so I might have missed something, is that you have the 2 separate processes for identifying the canopy gaps. Did you combine them at all?
Sure, we discussed it, and we went over it kind of with our project partner, and I think it would be more useful for what they're trying to accomplish to have one or the other.
I see.
And the results are fairly similar but different, as we discussed on that slide. And in areas where there's not LiDAR, you can rely on the image segmentation. So if we had combined it, we probably would have used some sort of fuzzy logic model to identify areas of overlap or give weight to areas that are adjacent to overlap.
Yeah, I was wondering, like, because you have the K-means with the vegetation. If you took the vegetation pixels, you could do a K-means with the LiDAR height there to do maybe 3, like for ground shrub trees.
Yeah,
It'd be kind of cool if it's available. You could have like a if it's available thing written into your code. I don't know. It's a cool project. I got excited about it.
Yeah. We definitely discussed that and went over that with also quite a bit, but just couldn't have time to dedicate to that stuff. So thank you.
Thanks for the idea.
Any other questions for our folks here? We've got a chat from Kiara. Thank you, Kiara, for helping out as the project partner for this.
So, I'll ask a question.
Third question.
So like, how do you think your approach to data analytics has changed as a result of taking Elsa's class over the last year?
Well, I didn't know anything to begin with, so I'm not from this domain, right? So for me, it's just trying to apply what I learned. Peter and my other different takes.
Just a lot more methodical and organized. My Python skills was very amateur before, and being able to look at large data sets and not be intimidated by them, I think.
Had you done any of the machine learning, like K-means stuff before this class?
Some,
No.
normal image segmentation things, but nothing. The K-means or the algorithm based stuff. Cool.
Yeah, I guess I'm also curious because I know there's a lot of GIS powerhouse in your group.
Chris on the call too.
And yep, hey Chris. So, yeah, I know both Chris and Peter, you've worked with that software a lot, so I'm curious, like as a GIS professional, like where do you think that having the coding skills is adding to that, and like could you see something like this QGIS workflow fitting into your kind of professional activities or something like it?
Yeah, I can start. I think being able to develop your own workflows based, if you have a large data set and you build your workflow around that, it's a lot more forgiving using a tool like Python than desktop GIS software. And I've already been using it professionally just to do large scale data processing and automate these tasks.
Awesome.
Chris can say something.
Yeah, for me, it was basically, it kind of seemed like when I was trying to get a lot of jobs that it just, even though that I had even prior experience in GIS, that it really wasn't enough for a lot of employers. And now I'm a lot more confident in what I'm able to do just with Python. And given that both Arc and QGIS work on a kind of Python backend, it informs me a lot, much more about how these programs are actually working at a much deeper level. And that just makes me feel a lot more confident in my own methods.
Well, thanks so much, guys. I want to, we're at our 1/3 mark, so let's move on. Getting some applause online. Lisa, did you want to go next?
Yeah, sure.
And then we'll finish up with. Okay, so.
Really up the presentation.
Yes, and. And. Okay, there we go. Oh, and you don't have the bar covering your presentation.
Just the navigation with the arrows or the click?
Usually work.
You just click back in the PowerPoint, it should go.
And maybe the click is how it's.
On this side, right?
Yeah.
Okay, good morning, everybody. My name is Luciana Palaszti, and I will talk about understanding societal impacts of large wildfires based on the ICS 209 daily current threat narratives. So let me show you these three numbers to start with. actually 2% of wildfires become these significant incidents that make it into this data set, but out of those two, they account for 85% of total suppression cost and around 95% of acres burned each year. So we can kind of start to have this sense of a very significant impact on the society, thinking about health, life, property, and all other physical values at risk, especially as we consider how wildfire activity has escalated and expected to escalate in the future, and how that puts more demand on management response, that the demand is also expected to increase for that. So when we think about these narrative reporting fields, it offers a previously non-synthesized valuable insight for fire management. And I want to emphasize this quote from Saint-Denis et al. 2023 of this critical moment, of this unique opportunity to gather this valuable insight about the relationship between the hazard characteristic, incident response, societal impacts, and threats incrementally across all phases of active response. So how do we link these geophysical fire metrics with the societal impacts and incident response? We focused on this interagency reporting tool, which is the ICS 209, which is the Incident Command System, a standard unseen all hazard incident management concept, which is part of a larger framework of which is the National Incident Management System. As I go forward, I will just refer to these incident status summaries and incident situation reports as ICS 209 as I discuss what they are about. So they are these informational snapshots that basically are first-hand observations to allow us to have a view into this decision-making process through the wide range of variables that are available in this data set. So here is an example of how an ICS 209 situation report might look like. And here you can see some of these fields, these individual fields that are available. And I want you to focus on these societal impact variables, the injuries and fatalities, and values at risk fields that are the narrative fields that we focused on, which are this wealth of buried narrative content that hasn't been analyzed before. So we decided to focus on two significant fires from 2021 and subsetted this ICS 209 plus data set to be able to focus on the current threat narrative fields, and Liz also did some analysis on the life safety and health status narrative fields. So to kind of give us an idea of where are these fires and what were the basic characteristics of these very significant fires that span across several counties and burned in California at an overlapping time. You can see these summaries here. But I want to focus on kind of how did we decide to focus on the 12-hour threat narratives and what kind of drove that decision. So when we looked at the reports and the time between these reports, we started to see this trend of how the frequency was mostly the highest frequency appeared around this 12-hour time frame. And especially when we put that into the context of time between reports and person containment, we saw that the reporting was the most frequent during the highest uncertainty when the fire was the least contained. And that's why we decided to focus on this 12-hour threat narrative, even though the 24, 48, 72 or greater than 72 narratives were also available. So I am not trying to go for the world record of the most text in one slide here, but I just wanted to give you this idea about how detailed one entry might be and to see how long they can be. So this is just an example from August 2021 for the Caldor fire. So you can really see this is a lot of text, even just for one entry to analyze. So as we started to explore the narrative, the data field for these test fires, we we're able to, even with very simple models, get a lot of entities per fire incident. You can see how a larger fire tend to have more entities, but even for the smaller, colder fire, we were able to pick up more than 1,000 entities based on this first graph. And when we started to look into, okay, like what are the distribution of those entities, what they might represent, we found a lot of entities relating to like kind of different geographic locations and other kind of types, even just based on this small English pipeline trained on a written web text. So when we think about like a simple, definitely more limited model and a more complex improved model, I am showing you some examples to kind of demonstrate what are the limitations of that. So first one, I used the limited, but I probably should have used wrong because this simple model was unable to pick up any of these entities, named entities, but when we actually used the larger, more complex model, we were able to get these categories already identified, where, for example, these species, we could have an idea of a category like critical habitat, although I want to mention that none of the models were able to pick up this cultural site, which can be interesting in terms of thinking about the societal impacts. So communities at risk might be an important aspect of this analysis, especially as we consider that the number of structures threatened is one of the most used fields in the ICS 209 research already. So being able to pick up, being able to mine the narrative text around the communities can be interesting to maybe connect these communities to already existing geophysical data and other aspects. But here, again, you can kind of see how a simple model really fails to be able to pick up these community names. But when we use the more powerful large language model, it was pretty successful in terms of picking up these communities and mine this from the narrative text. So here, I just kind of wanted to emphasize again how large language models, even without fine-tuning them or building customized pipelines, they are already able to create tables like this from a narrative text that you could see on that very messy slide. So here we can already have an idea of communities at risk, trying to think about categorizations of ecological risks. Although I kind of want to mention this, like, for example, this repetitive part here, which can be problematic, but definitely not something that we cannot control for as we fine-tune a model for our future uses. So where to focus next? Definitely the most important question is to think about how we can improve named entity recognition with large language models, especially as we consider and doing more about fine-tuning and customizing pipelines, which are complementary steps in adapting and optimizing large language models for these specific use cases, which could be this ICS 209 narrative text field mining. So eventually we would like to do that to build this metadata that can allow us to organize data according to threats, like we already started to see these emerging topics of, for example, ecological threats, communities at risk, infrastructure, or even like cultural threats and cultural sites that can be threatened, to eventually allow like a larger societal impact analysis based on these narrative fields across reports, but also across incidents to analyzing these fields. So thank you for your attention, and any questions?
Do you think it will make this easier or harder as people start to use large language models to write their original data? Do you think it'll make it easier because they understand it better, or harder because there's sort of different data?
Yeah, I think that's kind of a good question for sure from the standpoint of, I kind of worry about how like just our overall use of like AI will actually relate to how we create information going forward. Like that aspect, I think is still quite uncertain, and I don't think I have a good answer. But the most important thing I think is already keep considering those kinds of cases as we do research, so we know that it exists. Because that's the best I think we can do currently about predicting the future in that sense.
The other thing is this data set now spans 25 years.
Yeah.
And so there's this wealth of information that just has gone untapped.
What type of training data did you use or do you plan to use for the entity recognition?
Yeah, so we are in the phase of like deciding that like how to create the best kind of training data, especially after this like initial analysis, like already trying, like being able to pick up these topics, like have an idea of even just how to get started. Like it was pretty hard to like engage with these narrative fields, just like considering like even just from like 2 fires, we would have all of these named entities, like thousands of them from like a very huge amount of narrative content. So yeah, it's still kind of under development. It's definitely where we are going and trying to make those decisions to be able to improve on all of these, like, yeah, the ways, kind of the examples I have showed you before.
So this is really cool to see, because I think that I personally worked with ICS-209 data, and it's really, the narrative fields are not something I've really touched because they seem so messy. So it's a really useful tool to be able to like decipher these fields that contain a lot of information. So I have a couple of questions. How adaptable is your workflow to other search parameters or other categories, right? Like, are you able to kind of create it customized for different topics, that kind of thing? And then second, how could this be used to improve the 209s moving forward, in the sense of like, oh, you know, here's what we're seeing in this processing of the narrative and what makes it more difficult. And like, could you improve the ability of people who are actually writing these narratives to be more efficient, I guess, in how they're writing them?
Yeah, no, I think those are excellent questions that I also thought about before, even kind of going into like this whole effort to try to do this. I was thinking like, okay, like if we find and if we can define these named entities, would that have this like kind of feedback effect on how people would start reporting? I think that's kind of maybe also relating to like the question of like if AI is incorporated into even creating a report or something going forward, like how that kind of like creates this like communication between the two sources in that sense. So I don't think I have an answer for that, but I would expect that, for example, if we are able to like very reliably find that we really have these topics that show up not just in these 2 cases, but across the entire data set, that could actually maybe even guide the future reporting in the sense of like an extra field or another like kind of guideline in terms of, okay, like consider maybe putting in watersheds if they are at risk. So we can have this kind of like ecological thread already identified going forward. That's an expectation on the reporting side. But right now, these are just, they can put anything in there. So I think from that standpoint, it's messy, it's complex, but it has this huge opportunity to kind of go in there with an open mind and see what we find. And then based on what we find, try to make sense of, okay, like kind of putting in the expert opinion and the expert kind of views, but using large language models for this insane amount of narrative text that you just cannot read through with your human eye is really this opportunity that I think we would like to take on trying to keep exploring.
Cool.
Just to add to that, I think you captured that really well. I also think there's this opportunity, bigger picture, being able to simplify and condense down the narratives that are in there and roll them up to the incident level, making it a lot easier for people to see what happens chronologically over time.
Yeah, because you're talking about, you know, potentially the feedback loop of creating, oh, maybe we need an attribute column now that defines some of these things like neighborhoods at risk or watersheds or whatever. That could also be something that's done post-processing, right?
That's what I'm thinking of, is building that into some metadata that then could be used to access that.
Yeah, like for example, the community is at risk in the sense like how they can relate to the number of damaged structures or threatened structures. Like we only have a number about those, but we don't really know what's the distribution, where are those. So like maybe being able to link that to these communities, like when you have the community name, like be able to like kind of geolocate them eventually and then putting them on the map with those like structures threatened and start to have maybe an idea of a distribution of them would be very cool and kind of give this like kind of really act as this like hopefully revolution of the narrative text with the geophysical data, like really giving this more complex story of what happens based on these ICS 209 data reports.
In ecology, we talk a lot about presence and absence data. Like it's easy to say where you did find something, but it's hard to say where something isn't, especially from just that kind of data. So it seems like you have the same sort of problem with voluntary, fields of data where people are just putting it in there voluntarily, so you know where it is, but you don't know where something isn't. So specifically when we're talking about like social inequity or things, how do we deal with just that fact that we're getting sort of a bias on what people want to tell us?
Yeah, definitely. Like the bias part in terms of this reporting is something that if I had a little more time, probably I should have mentioned when I am introducing the whole idea of ICS 209. Why is it done, and how these like how people use ICS 209 to even like maybe lobby for more resources or try to use that as a tool to really target and direct resources, especially when we have competing like management demands in terms of these fires happening at the same time and happening like more frequently, and we always have this competition of resources. So that bias is in the data. So we have to deal with that in a meaningful way, that we haven't really explored in that sense. But still, like having this like at least what I think right now is that having this kind of like voluntary reporting, still like being able to pick up like ecological threats, like the slide when I had those species, I think that can be valuable, or even like cultural like sites, like we see like mentions of, for example, like Native American cultural sites and all of those kind of narrative texts that even if it's biased, I feel like it's one of the first time those kinds of like threats actually show up in terms of reporting about fire and impacts and societal impacts. So just kind of like scratching the surface, like showing that it's already there, even if in a biased way, I think would help us going forward to create a more just and more equitable reporting in the sense of what are the actual threats and damages and the impacts of these fires that we have been seeing and continue to see.
Yeah. Do you think it would be possible to like compare the narrative and the ICS? Oh, sorry. Go ahead.
Can I have you
Yeah.
get together afterwards?
Yeah.
We have one more presentation I want to get to before the end of the hour, but
Thank you.
everybody's for the great discussion. And you guys know where to find Luxa, right? Over there. All right. Oh. All right, looks like. Sorry, I guess we didn't, I guess the presenter screen was showing up on Zoom. But hopefully. Oh. That works. Okay. Sky, we're seeing your screen, but kind of.
Is it small or is it big?
Let me. Oh, okay. Okay, so here we are in Zoom. There's your screen. Any chance, Sky, that you can, I feel like I remember you have a really giant monitor. Can you make the window smaller? Because it's showing up at like a quarter of the size.
Really?
Of our screen here.
Let's see, let's do
It
this.
looks like it's really long.
Is that working?
Horizontal.
Oh, it's always something.
Sky saw it.
Share. That's not working now.
And also if you're talking, it's not coming through.
Oh, for the
Yeah.
love of crikey.
You're getting a little bit of noise, I think.
So you're not hearing me now?
I wonder if that's actually the sound from here.
Do you not hear me?
I think it might be on our end.
Try again.
Zoom can hear everything. Just the app, right?
It's on our end.
All right. All right, it's definitely on our end, Sky, so.
Oh, good.
Oh, wait, that's you coming out of my computer. Can everybody hear that?
Yeah, I can hear him online.
Hear me now?
Yeah, that's it.
Right.
Casey to the rescue.
All right.
Is it working?
Yeah.
Yes.
I can't see anything. So might go, Elsa?
Yes, we can hear you now. Screen's still a little small, but
I shared it by I mean, I guess we could do your I just have to toggle some slides. That's why I want to do it myself, but I mean,
oh, okay.
sure what you're here. I am sharing by application.
Why don't I share it and I can toggle the slides if we
Okay, that's fine. Let's go with that. Let me stop sharing.
All right. Sorry for the delay, everybody. Okay. That's full screen. Now let's share it. Okay, does that look good to everybody?
We good?
Great.
There you are.
You are set to go.
Okay, good morning, everyone. My name is Sky Corbett, and I work with the USGS. I've been working with the USGS for roughly 14 years. I got my master's in geology, and my focus at work is basically on remote sensing and spatial analysis, providing insights into spatial distribution of landslide risk. I got the joy of having lots of toys, terrestrial LiDAR, UAVs, and I do a lot of instrumentation, and so I get to have fun in the field, create pretty pictures, and work with the research scientists and working together. I'm a really slow writer, so it's the perfect blend. I love it. Elsa was kind enough to work with me on this project. I had lots of field work, and so it was hard working together, but she was very patient. So thank you very much, Elsa. Today's top presentation is Detecting the Unseen Landslides, Integrating Storm, Hydrometeorology, and Satellite Data for Prediction and Detection. Next slide, please. The exact percentage of landslides detected versus the actual number that occurs in California is challenging due to the variability in detection methods and reporting accuracy. The detection of landslides largely depends on the technology used, such as satellite imagery aerial surveys, and ground-based observations. Despite advancements, many smaller landslides go undetected, especially in remote or forested areas. And so consequently, the more we can detect landslides and understand the conditions that precede them, the better we can model forecast, ultimately benefiting society. And so the three images you're seeing here, the one on your left, are reported landslides that occurred during the January 2023 atmospheric river system. And I would say 100% of those are actually reported by either landowners reporting landslides on their property or adjacent to their property, or police people that are reporting landslides along roadways. And both those images on your right are of actual images in the Northern California, San Francisco Bay Area during those January storms. Next slide, please. So for my project, I basically broke it down into two models. There's the A-star model, which identifies soil moisture anomalies to predict landslide risk, and then which is the prediction model. And then there's the detection model, which is the Opera disturbance product, which provides detailed satellite imagery that identifies changes in land cover and surface conditions. And just I want to get through the acronyms really quickly, so because NASA loves their acronyms. This is LPDAC. LPDAC is the Land Processes Distributed Active Archive Center. It's a partnership between the USGS and NASA, and it's a component of NASA's Earth Observing System Data and Information System. Then there's OPERA, and OPERA is the Observational Products for End Users for Remote Sensing Analysis. And for this project, I was using OPERA's Land Surface Disturbance Alert version 1 data product. Next slide, please. So the A-star model. The A-star model leverages soil moisture anomalies to predict the likelihood of landslides. By comparing current soil moisture to historical norms and adjusting for typical variability. The A-star model identifies areas where the soil is significantly wetter or drier than usual, indicating potential landslide risk. And to calculate the A-star, we use the antecedent water index, and that is basically a measure used to quantify the moisture content in soil prior to a significant precipitation event. So we use the antecedent water index to simulate soil moisture. We then calculate the average soil moisture for each day over 15 years. So that would be our AWI reoccurrence interval. Then we compare today's soil moisture to this average to find the anomaly. We adjust the anomaly to make it a standard measure, which is A-star. And then we set a threshold for A-star to identify high landslide risk areas. And we used historical landslide data to create the threshold of areas that have high risk. And so the image on your right is basically the last figure that the A-star model spits out. And it's the threshold here being 1 to roughly 1.7. And it's going from light yellow to very dark red. And where the very dark red is a very high probability of landslides occurring in that area for that particular rain event. Next slide, please. And then once we have these areas that with the high probability, I then build bounding boxes around them so I could use it in the next model, the Opera disturbance data. Next slide, please. So with those bounding boxes, I then bring it into LPDAC's Opera Disturbance Alert. And so the Opera Disturbance Alert is a powerful tool for monitoring land surface changes. It combines data from harmonized Landsat and Sentinel-2 satellites, providing observations every 2 to 4 days at a 30-meter resolution. So 2 to 4 days, that's great. So it's every week to sub-weekly, it's picking up data. But sometimes the cloud cover is way too thick, and so you're not going to see anything at all, but at least we know it's repetitive. The rub here is that it's 30-meter resolution. So it's pretty rough, but we'll see that we're able to detect some landslides. And this figure here It's my triptych, but I really want you to focus on the vegetation disturbance status. So here what you're seeing is you're seeing disturbed vegetation between the dates of October 1st, 2022 to February 8th, 2023. And so the next couple of slides, what we're going to do is we're going to pick an area in the southeast corner of this data and just kind of go close up and look at imagery and see if we see change. Is there actual change occurring? Next slide, please. So here is kind of going closer up in this purple polygon. We're going to go even closer, but this I want to show you is now we're looking at change that has occurred between January 1st and February 1st, 2023. I wanted to close that window more, but I was really having a hard time making the reds and yellows pop out. It just kind of blended in. So I chose kind of this month of disturbance to actually for visualization here. So there's the purple polygon. Next slide, please. So here's an image from November 23rd, 2022. Next image, please. And then we're overlaid the disturbance raster. And so, oh, I'm not gonna be able to circle it with my mouse. Disregard, so I'll just talk it through. Disregard that the long red is basically fluvial erosion. And then there's that blob right in the middle. Thank you, Elsa. Yeah, the blob right in the lower, that one, yes. That is a pond filling up with water, but all the little speckles, that speckle a little bit lower, further south, that speckle, and then to the, yes, to the west, that speckle. I really want you to take a look at those areas. So Elsa, if you'll go forward and go back. And so the image, the greener image is an image from January 5th, 2023. And if you go back, oops, it just toggled. So I really am trying to show that we are detecting landslides and they're basically debris flows and they're not that big. And so even with this coarse resolution, we are seeing change. That's like a win for me. And so final slide, please. So using the A-star model in conjunction with Opera's disturbance product represents a novel and effective way to map landslides, offering significant improvements in prediction accuracy, timely detection, and comprehensive risk management. This innovative approach enhances our ability to prepare for and respond to landslide events, ultimately contributing to better hazard mitigation and safety measures. So what I'm hoping to do this coming rain year is that I want to start applying the A-star model. So October occurs, and that's in California. We start getting our initial rains. So we'll start filling our A-star bucket of water. And then as the rainy season continues, we should start seeing that threshold being passed. So we should see areas of high probability where landslides could occur. And once we see those areas of high probability, then taking those bounding boxes to the Opera disturbance files and seeing, can we detect these landslides occurring? This is really preliminary. As you can tell through the disturbance file, I got to do some filtering, take out the fluvial erosion areas, maybe apply a slope model because landslides occur at steeper slopes. So there's a bunch of work that needs to happen, but the preliminary project shows that it's possible. And so the hope is the more that we could have these what we call jelly bean landslide maps, we know where these landslides are occurring, so we can model more and create better models to help the society and overall. Next slide, please. And here are my references for my project, and that is it. Thank you very much.
Awesome. Any questions in the room or Allison? Yeah.
That was really great. Good job explaining it all.
Thank you.
I'm curious about the soil moisture that you use. How deep is that data product?
So it's not a data product. So what we're doing, we're using precipitation as a proxy for soil moisture. So it's basically, I'm thinking of it as a bucket. We're filling that bucket up, and eventually that bucket will overflow, but it's also draining as well. So it's just it's a proxy for looking at soil moisture.
Really interesting. Okay. Cool. Thank you.
Very welcome.
I have a question. What sort of application would you see, or let me rephrase that. How do you think you could apply this to like a more slower gradual process like soil creep?
Oh, that'd be tough. I mean, the opera disturbance files will not pick that up as fast. It maybe in a long term you see it. And also with soil creep, usually you see these larger earth flows, they flow in the summertime.
Yeah.
So you have to do a different, maybe stage it differently, I'm sure.
Yeah, you probably have to have a much longer data set.
Right.
Yeah.
It'd be interesting though.
I want to just ask a little more about the predictability part. You said since the data are coming from precipitation data, presumably we have good future projections of that. Is there any use in using this method to sort of look at 10 or 15 or 20 years ahead at where the big landslide places are?
Good. Well, so the A-star model is actually using current precipitation, and we're comparing that to the 15-year reoccurrence interval. What I'm not even trying to actually do future kind of modeling. My idea for this is just to get to look at current slide action, for lack of a better term. So I'm not sure if that's possible.
Oh, yeah, same question.
Yeah, I was also just curious what you think you would need to be able to predict into the future. So similar.
I think this model would help predict because right now, like as I said in the beginning of the presentation, the reporting of landslides is primary. I mean, for the most part, NASA does have this overarching kind of landslides are occurring here, and they're using different tools. But a lot of the landslides being reported are either from individual landowners or police people. So if we're able to say these smaller, and I'm actually looking at smaller landslides, where they're occurring and what conditions cause them, then that would help modelers we'd have more data, more historical data, which would help modelers then help take that further to predict, I would say.
How much are landslides an ecological feature? Like how well do they correlate with the vegetation type and the soil type? Like can we predict them by ecotone essentially, or ecotype or bio?
So I know I could talk for the Bay Area and California in general, where landslides are occurring in basically these hill slopes are grassy hill slopes. And it's like usually the soil it's soil mantle landscape. So there's usually a meter or more of soil on top of bedrock in hollows. So yes and no, I would say to that. For this project, I'm primarily focusing on California, trying to keep it smaller. I think you could create ecological zones of where you could predict landslides, yes. I mean, they're going to be in higher slope areas, soil mantle landscape, but that would be it's a generalization, of course.
And it's very hard to know because we don't have very good or complete landslide data. Your evidence of absence problem is enormous.
Oh, right.
Yeah, so awesome. Thank you so much, Sky. If anybody has any further questions for any of our groups, let me know, or I guess you could email them to EarthLab if you don't know how to contact me. And I will pass those along and get you in touch. But yeah, fantastic work, everybody. Amazing projects and really great presentations. And thank you to everybody who's here in person and online. Take care. We really appreciate it.